So yeah, so just keep comments on each presentation, and I will share your comments to the presenter, but without your name, so so that your privacy will be kept, but just make comments. Concrete comments is better. If great presentation, so that can apply for any presentation. So the more specific comments are appreciated. Typically, just maybe the 2 or 3 lines. That's enough. But yeah. Okay, so now maybe that we start the presentation, and the first presentation by Andrew. Okay, so you can start now.
Good to go?
Yep.
Okay. All right. Hello, everyone. My name is Andrew, and my project is analyzing different models that can be used to predict the net worth of an individual, specifically through multiple linear regression, ridge regression, and lasso regression. So first, my slide schedule for the presentation today. I'll start with an introduction of my topic. Next, I'll go through the data description of where I got the data from and how I manipulated it. Next, I will give the methodologies used for each 3 of the models that I built. So ridge, lasso, and linear regression. And then I will go into the results analysis and explain the pros and cons of each method, and also how they relate in terms of bias variance trade-off. And then finally, at the end, I will give an overall summary on the presentation. So to start, introduction. For my data, I used a survey where each year the Federal Reserve conducts, it's called a survey of consumer finances, and basically it polls individuals throughout the United States and takes data on all sorts of personal finance issues like assets, liabilities, income, debt, you name it. So the variable that I looked at as my dependent variable is net worth. So this is just defined as an individual's assets minus their liabilities. So if they had 100,000 assets, 50,000 liabilities, their net worth would be 50,000. So after I defined what I was using as my dependent variable, I used 3 different models in order to predict net worth, which I stated earlier using the 3 regression techniques. So MLR, ridge, and lasso. And then after that, I analyzed, because these are 3 different methods, we have different coefficient estimates. And I wanted to look at how are these different coefficient estimates different in terms of their bias variance trade-off, and how does that apply to the different methods. So my data was extracted from the Federal Reserve website. Oh, my bad. Go back. I accidentally skipped ahead. So the data set was quite large. It included 28,885 observations and 351 variables. So I did a lot of data sorting, and after looking through and some of Kaz's suggestions, some of the variables included trivial relationships, and those were excluded, such as assets, which, for example, if you just look at assets, that's easily going to explain someone's net worth, and the same way around. If you just look at their net worth, they're likely to have high assets. So I excluded variables with trivial relationships. And from there, I started by building my base model with just simple multiple linear regression. So I looked at which variables are statistically significant based on p-value, and I ended up with a model using 16 hand-selected variables from the data. So what were the variables that I used? Well, as I stated before, the dependent variable is net worth, which is continuous, meaning it's on a scale from 0 to infinity. And then we had both continuous and categorical independent variables. So The continuous variables were amount in checking account, amount in savings account, amount in stocks, cash, vehicle value, bonds, home equity, debt to income ratio, amount in trusts, pension amount, CDs, and a unique one that I actually found was significant was the value of food that an individual had in their home. And then the categorical variables were married, education level, number of kids, race, and age. So first, looking at my response variable, as stated before, the net worth was that dependent variable I was looking at. So originally, the just net worth by itself was extremely right skewed, as shown in the left density chart here. So my first thought was just apply logarithmic transformation, but that was giving me issues because many of the individuals had liabilities greater than their assets, so they had a negative net worth. So we can't take log of negative numbers. So I first had to take logarithm of absolute value of the net worth. And additionally, because many people had reported a net worth of 0, that was giving me issues because I was taking log of 0. So I had to apply a second transformation, adding the constant of 1. So after I did that, applied log of absolute value of net worth plus 1, I was able to come up with a new variable. I just called it log dot net worth. And this variable was much similar to a normal distribution, but not exactly a bell curve, but it was much easier to work with and more feasible for me to use. So next, after I transform the dependent variable, we'll start building our models. So the method that I used first was ridge regression. So if we remember from class, the goal is to minimize this expression, regression sum of squares plus lambda times the sum of the coefficients squared, where our lambda is the tuning parameter. So if lambda is 0, then our ridge result is going to be the same as ordinary least squares. So essentially the idea with this method is to penalize a large sum of squares. So ultimately we want to shrink the model. So if lambda is large, then our coefficients are going to be smaller. If lambda is smaller, then the sum of our coefficients will be larger. So it's a shrinkage method, essentially. Similarly, with lasso regression, our goal is to minimize our regression sum of squares, but in this case, we have lambda times the sum of the absolute value of our coefficients. So we have the same parameters here, lambda, and one small difference between lasso and ridge regression is with lasso regression, the coefficients can shrink all the way down to 0. So lasso can yield a little bit simpler results than ridge regression in that sense, but the two methods are very similar. So moving on to results of these methods. So the first model I used just simple multiple linear regression. As you can see up top in the R code, we just use the LM function of our dependent variable regressed on the 16 independent variables that I mentioned before. And then I show a summary here of our model. So all of these variables are statistically significant based on the p-value. Another important thing to note, to test for multi-collinearity, I used variance inflation factors down below. So VIF of our model. So I believe we covered this in class. Anything over a variance inflation factor over 5 means that the model built suffers heavily from like linear combinations of each other. So that's not going to be good in our predictive accuracy. So since each of our variables has a VIF less than 5, that's a good sign that our model is not going to be suffering from multi-collinearity in this case. Now onto the fun model. We have our ridge regression. So this model was very fun to build. So I first started by using the GLM net function, which is just used to fit a generalized linear model via the penalization that I mentioned earlier. So how we do this is split into test data, training data, and then we're going to use cross-validation to determine the value of lambda that minimizes our error. So I get the lambda value first here by, I just called it optimal lambda from our data set. And it's quite high, which is expected because our number of observations are very high. So after I find the optimal lambda, what I did is build our ridge model down here by substituting our value for the optimal lambda into the ridge equation. And then from there, I'm able to project the coefficients from this model. So as you can see, these coefficients are smaller than that, are closer to 0 than that of the multiple linear regression model, which is expected. And then on the right here, we have the graph of the different values of lambda. So the x-axis is the log of lambda. So because lambda is so large, it's easier to interpret by looking at the log of it on the x-axis. So if we take log of the 402.4138, that's right around 18.2 right here. And that's going to be our value of lambda that minimizes the mean squared error. So next, going on to the procedure for lasso regression. So this was a similar procedure to find the optimal lambda, and same thing, substituting that back in to get the, I call it the optimal lasso model. However, there's a couple differences between the two methods. So notice for the lasso regression, several of our coefficients have shrunk to 0. So our checking variable and also our married variable are both shrunk to 0. Additionally, the best lambda value that minimizes the MSE in this case is 290,000, which is much less than the one that we found for ridge. And this implies that lasso is creating a more flexible model because we know lambda is inversely related to the flexibility. So in this case, in the lasso regression model, we have a smaller lambda. So a smaller lambda implies a more flexible model. So the lasso regression model is much similar to the multiple linear regression in terms of flexibility. And the ridge model is the least flexible of the three. So looking at our results, I really wanted to analyze how does the bias variance trade-off apply to all three of these methods. So with ridge and lasso, we're looking to find that lambda that minimizes the cross-validation error. So because we're shrinking the coefficients, the model is much less flexible. And on the other hand, the bias of the model is much higher because we're manipulating the coefficients. So with multiple linear regression, it's kind of the opposite. So we have a very flexible model, but a much higher variance and lower bias.
Excuse me, 1 minute left.
4?
1 minute left.
Oh, okay. I have 2 more slides.
Yep.
So moving on to our summary, the main idea of using these 3 different models is to show no matter what situation we have, the bias variance trade-off always applies. So we can't have a model with both low variance and low bias at the same time. However, there are different situations where shrinkage or MLR might want to be used. MLR is obviously a bit easier to use. However, shrinkage in this, it was more beneficial in this case because number of predictors is very, very large. So we want to simplify the model, which is why the shrinkage is good for this situation. I don't want to go over, but thank you very much for listening.
Oh, thank you, Andrew. And I would like that some of 1 or 2 of you ask him short questions. Anyone?
Well, I just have one short question. In the first model, I think the variable called vehicles had a negative sign. How do you interpret that? The negative sign of vehicle to the asset? I think maybe it should be positive.
Which variable?
I think it was vehicle, VEHI, vehicle number or something.
Yes, that is let me see. Was it the multiple linear regression?
Yes, I think this is the first model.
Yeah, it is interesting. So I thought it's negative because the vehicle variable is the amount of money that a person has tied up in their vehicle. So to me, I interpreted that as if an individual is spending a lot on fancy cars, then maybe that is contributing less to their net worth and they're prone to spending more. But that was one thing that did stick out to me as well. So that was my interpretation, but I do not know exactly why it is negative.
Okay, thank you.
Yeah. I once heard that the millionaires have not really their expensive cars. So
Yeah. So
yeah,
possibly
it's interesting.
if they are spending, it makes sense because if the higher the net worth, they're spending more on stocks, bonds, they're more into investing instead of spending on vehicles. I
Yeah.
guess that would be how I would interpret it.
Quick question. So like, let me know if I'm interpreting this wrong, but like, do you think it might be because like the vehicle, like cost of like the value of a vehicle depreciates like quicker than like other things? Do you think that might also be it, or is it just?
Yeah, because most of the other variables are investments that are going to appreciate over time. So that's a really good point because if you buy a vehicle over time, it's going to depreciate. Yeah, that makes sense.
Yeah.
Thanks.
Good point.
Any other questions?
I was wondering if you could go back to at the very beginning, you're explaining the like logarithmic transformation or however you'd call it for the values. I was a little confused on that. So did you say that some of them had negative net worths?
Yeah, because it's a survey of everyone. So net worth, you say you're in debt, like say you have a mortgage and you have no investments at all, your liabilities are greater than your assets, so your net worth would be negative in that case. I didn't actually think about that either until I started looking at the data and trying to take logarithm, and it kept giving me errors. So yeah, that's why some had negative net worths, because they had debts that are higher than any of their investments.
Okay, thank you.
Yeah. Maybe some people argue that transformation because the negative assets are treated as the same as the positive assets. So
right, I tried it that way. I tried it that way by keeping the negatives in there, but it was even worse of a skew. So
that's
that
right.
was what I settled on.
Yeah, I think that probably the only possible way is to the censor some variable, maybe below zero, that we just we make a model with a point mass at the zero. Then possibly we can deal with it, but I think it's much harder than usual model. So yeah.
Yeah, that's what I tried, but it wasn't working. Or even just doing like 1 over net worth, it still wasn't working. But
yeah.
Have you tried doing the analysis where like you set all of the negative variables as like 0 plus 1? I mean, that might also cause a skew too.
Yeah, I tried that as well. Like, so what I did was I looked at the minimum, like whatever the minimum number negative was, and then I added that number. So like say the minimum net worth was negative 100,000. What I did was log of net worth plus 100,000 and then everything would be positive, right?
Oh, okay.
Is that what you're saying or no?
Oh, that actually is a better interpretation than what I was doing. I was gonna say like if anything is negative, you just set it as equal to 1, but then that would that would cause a better skew. But I think that sounds. How did that work out? Did you do that one?
Then it was really skewed to the left after that.
Okay.
So I think if I had to do it over, I'd use maybe a little easier data.
Mhm.
But I think it worked out good still.
I appreciate the in-depth answer.
Yeah, I think that's. I think the Colin asked a good question. Yeah, yeah. So, so I think that probably the most arguable transformation here. So, yeah, I think that it's, if you want to investigate this problem more, maybe you can investigate that transformation part.
Yeah.
Yeah. Okay. Thank you.
Thank you.
Okay. So next, we have only 4 presentations, so a little
I
good.
can go next.
So the anyone who will go second?
I can go next.
Okay, so Walid, can you share the screen?
Yeah, sure. He should stop sharing screen, Andrew. Can you guys hear me well?
Yes.
Okay. I mean, Andrew, he has stopped sharing the screen. Oh, okay.
Are you able to now?
Yeah.
Okay.
Can you see my screen now, right?
Yes, you can start.
Okay. Okay, I'll start now. Hello, everyone. My name is Walid Ali Kwan. I am a senior undergraduate student at College of Engineering. Today, I will present a statistical analysis of Airbnb prices using random forest regression. So my project outline is as follows. We will begin by speaking about the project introduction and objectives. Then we will talk about data and modifications, then analysis methodologies using random forest, lastly, empirical results and conclusion. Introduction. Statistical analysis will be performed for a list of over 74,000 Airbnb prices. The statistical analysis will evaluate a subset of the 29 features present in the dataset. And one of the reasons why I chose this data is because I use Airbnb when I travel. So I am eager to know how the price is predicted based on what variables. Project objectives. So objective 1, I will use the review scores to predict if Airbnb apartments or houses have a higher price towards making a prediction. Also, I will attempt to use the cleaning fees and cancellation policies to predict the cost. Objective 2, we will compare a model with the review and a model without review by prediction performance using 2 linear models. So objective 2 here, we would basically have needed to already do objective 1 implicitly. So objective 1, as we mentioned, we were building a model and making prediction, and objective 2, we will take those prediction and evaluates them. Data sources were obtained from Kaggle. Link is provided. The data contains 74,000. 112 samples and 29 variables. The data consists of Airbnb prices and includes features and capabilities for each apartment and house. The data is displayed as Excel file. So here we have some of the description of the variables. Log price accommodates room type, bathrooms, bedrooms, host sends are all dependent variable, whereas the property type is independent. So log price is actually the price of Airbnb. Accommodates here, we need to know that is how many people they are allowed in the house. Data modifications. We double check if columns have not available or missing values that are driving the activity, in which case we would be better off to get rid of those columns. A benchmark is for more than 30% of values are not available for that column, we also get rid of it. The define function in a omit seems to be super aggressive, which eliminated 50% of the training data. So we identify where the missing data coming from, but however, the majority don't have missing data. For example, host response rate, first review, and review scores have greater than 20% missing data. So this suggests we want to remove these columns and we do our analysis. Methodologies, variables we probably don't want. So in general, any continuous variables quantitative we can include. If it is not good, we can get rid of it. For factors, for example, things with a certain numbers of levels or things with effectively strings, we need to be more selective. So for example, here on the slides we have, so those are bad for the following reasons. So description, zip code, name, because effectively it is a factor with as many levels as rows. Methodologies treating factor variables as factors. Here we did, for example, room type being what is considered a vector of string. It should instead be treated as a factor. So R can treat that variable appropriately. So we have string data, for example, property type, cancellation policies, and so on. Normally, we cannot run a regression on string data, factor data with the multiple levels. So R and its algorithms will convert those factor variables into indicator variables. So making a test data, in order to calculate test error, we need to actually create test data, which we don't have here typically. Then we want to take our existing data and randomly choose a subset as the trained data and choose the other subset as the test data. But we are giving the data in one shot. There is not separated train or test. So we need to do a train and test split. So for the next slide, for example, we're gonna have a scatter plot of some of our empirical results. So we have quantitative, numerical, continuous, like log price, bedrooms, and factors such as property type, anything with a string. So to interrupt this graph, let me see if I can annotate. So all the top variables here are our X values, and on the right screen we have Y values. So this plots works in pairs. Each column corresponds to a particular variable, and similarly each row corresponds to a particular variable. The diagonal has the same row feature and column feature itself. So GG pairs will show the distribution of what variable. For example, looking at the first column, log price here, and second row accommodates. We will see scatter plot of the two. So accommodates should be here. Looking, for example, at the mirror along the diagonal, so let's say the second row accommodates. Sorry, so for the second column, we have correlation of the value 0.590. That's and the log price. So here, for example, if you go to Airbnb, we can interpret this as the more people in the house, the higher the price would be. So we know that the correlation goes between -1 and 1. Then it implies there is a strong relationship relative to the target, to the log price. Go to the second slide. Okay, so for this slide, it is empirical results, distribution of the trained data features for both quantitative and qualitative factor features. So here we will incorporate a mixture of the two. So note that the primary interest is to compare continuous variables such as log price with some factor variables, room type. Looking at the cell corresponding to the column containing room type and the row corresponding to the log price. We note that for each level of room type, for example, entire home, and maybe you can see it is right in the bottom here, and private room, shared room, we get separate box plot of log price, which is here. So as data scientists, we can craft a story, or we can say that in general, that like on top here is going to be 75 7th, and here is 25th. Here and the middle is the median. Is higher for the room types corresponding to more of the home. So basically, people prefer to have entire home in Airbnb, but the price would be much higher. Further, we can also then doing this, each level of factor has its own box plot. As such, we only want to include factors that don't have too many levels.
2 minutes
for example,
left. Sorry, 2 minutes left.
I only have 2 slides more. Okay, thank you. So for example, let's look at the cancellation policy. So the more strict cancellation policy, the higher the price would be for Airbnb. Cancellation policies has 5 box plots. Okay. Okay, so for the here I did 2 tests. I did model A and model B. So we want to know which one has a better fit than the other. So for example, model B let's say model 2 is better than A. If B is better than A, then we all means we use B, which in case it's model with additional features. So model A, for example, doesn't have review as features. B has a permutation, a model that is similar to A, except that it's all additional feature review. So our choice, we chose mean square error. Whichever has the lowest mean square error, it has it fit better than the other model. So I realize here as MSE of model 2 has the number of reviews is better than it is what it has a smaller mean square error, but looking at the variable importance plot for the random forest, I can see that number of reviews was on some level the least important, which surprises me here.
So wrap up your presentation.
Yeah, just conclusion and I'll be done. Conclusion, objective 1, we would have mentioned building a model and making prediction. Objective 2 takes those prediction and evaluates them. Linear regression, we can do statistical tests on variables to say they are statistically significant, and nonlinear regression such as random forest, decision tree. It's we only say that what are important, not are important relative measures. Thank you all for listening.
So thank you, Walid. So
Yeah.
anyone has any questions?
Sorry, I took longer time because when I annotate, I need a little bit time to stop annotating and go to the next slide. So
I got a quick question. Where'd you get the data for this?
Kaggle.
Oh, okay, cool.
Okay. See Kaggle.
Oh, my bad.
Ah.
Any other questions?
Can I see the I think it was a cancellation policy. Was it?
Okay. For this one?
Yeah, could you explain that one again? Was it a higher?
Okay, so on the bottom here we see strict cancellation policy.
Mm-hmm.
So if you cancel, if you for example cancel your Airbnb, so the cancellation, I mean the price will be higher. So you'll have to pay more cancellation fees. That's what it means. So that's why this scatter plot here.
Okay. So the more
is higher.
Right. So the stricter they
I
are.
don't know. Yeah. So if you can, I don't know. I cannot annotate now, but like if you see the box is going a little bit up, and if you can see the Y value on the left side, the number goes up.
Yeah, that makes sense.
Okay.
Thank you.
Sorry, I have a question about empirical results. So besides the plots, you have shown that the graph for the node purity or node impurity. So you tried the random forest and how about other models did you try other models?
Mostly I tried random forest.
Uh-huh.
So and then that's I got those graphs, and then based on that.
Okay, so can you show the results for the random forest, the slides for the results of random forest again?
Okay.
Okay, so I'm not exactly sure what you did.
Okay, 1 second.
So just you put all variables. Oh, yep.
Sorry, for this one.
Do you have any other slides for the random forest results?
I
This
have
is
those.
descriptive, right?
Mhm.
So, okay, so just go back to the random forest result. So I'm not exactly sure what you did. So you just put all variables at once?
For which one? For this slide?
Yeah.
No, here I tried to see like which variables that determine the price of. So for example,
I see.
here I'm okay. For here I made model A and B. Model 1 is, for example, doesn't have review, and B, for example, is similar to A, but it has additional features.
So you, I think in the earlier you said that you compare the model with reviews and without reviews, right? But you didn't do that. But you put all variables and you basically describe which variable explains more.
Yeah.
Okay.
Because based on that, I am using test error to say that evaluate how B and A perform on the test data.
Okay. So you covered all slides, or you created?
Sorry?
You covered all slides you created?
Yeah.
Okay.
Yeah.
Okay, great. Okay, so thank you, Walid. So next, maybe who goes next?
I can go next.
Okay, so Caitlin. So the Walid, oh yeah, okay, that's fine. So you can share the screen now.
How do I share my screen?
You have the green button at the bottom, probably. Yep.
Does that work?
Yep, I can see the screen now. Okay, you can start.
I don't know how to. There we go. So my name is Caitlin, and I did my project on autism rates and air pollution. This is just an outline of what I'm going to be talking about. And then, so it's theorized that there is a relationship between air pollution exposure in utero and an increased risk of autism. And I wanted to see if that relationship is strong enough where you could predict the rates of autism. So the Autism and Developmental Disability Network did a really good job of measuring the autism rates of 8-year-olds in various cities across America between 2004 and 2014. They did like every other year in a bunch of different counties and cities. Not all of the counties and cities were in every single year, but they each had at least 2 years involved. And then I found some really good data on air pollution from the EPA. And I think I have that in the next slide. So they had data for unhealthy days, which they didn't really specify what they qualified as an unhealthy day, but they had it qualified from very unhealthy to a good day, and I just added up the unhealthiest days to make up that variable. And then for carbon monoxide was my next air pollutant, and I just did the 8-hour max average for that year. Same thing for ozone. For nitrogen dioxide, I did the annual mean. For sulfur dioxide, I did the annual mean. And then parts per million, that is less than 2.5 microns, and parts per million, which is less than 10 microns. And I was able to find data for that for all of the years I needed. And how I picked the years for the air pollution was I just went back 8 years from when the autism rates were calculated, because it was done in 8-year-olds and I need to see how they were affected in utero. So this is just the trend of the air pollution rates over the years. And as you can see, these are very steady. And that was kind of concerning because if I go back, I have a chart on the autism rates over the years, and these are going up. So I had a feeling that they might not be as correlated as I initially thought. So my analysis plan was to use multiple linear regression to find a model, and then use the step function to find the model with the lowest AIC, and then use k-fold cross-validation to determine the accuracy of that model. And then I ran into an issue with the parts per million 2.5 size. So in the years 1996 and 1998, the EPA didn't record those values. So I ended up with a lot of rows with missing values. And then when I did that analysis, those rows were deleted. So the first time around, I had a bunch of missing rows, and I thought that that might lead to a less accurate model. So I decided to run my plan again, but I just deleted the whole column of the 2.5 size, just to see if that might yield a more accurate result. So here I have the correlation. Just, on the x-axis, I have the pollution rates, and on the y-axis, I have the autism rates, and they're not correlated. They're not even like non-linearly correlated. But at this point, I had, all my data put together. I had to go through and make sure that I had, the air pollution picked from the right counties, make sure it lined up with where the autism studies were done. But yeah, it's just pretty evenly distributed. This for CO2 or for carbon monoxide, at first glance, it looks like it's maybe negatively related, but most of the data is just in this corner. So I feel like that was just sort of a fluke, having this kind of line of correlation here. So for my analysis, I just did what I said. I ran some linear regression models, and the model that yielded the best predictors were the air quality index days, ozone, and SO2. And then I did cross-validation with k equals 5, and I ended up with a RMSE of 3.28 and an R squared of 0.27. I did the same thing for the data without the 2.5 measure. And again, I used backward selection to find the model with the lowest AIC, but this time I had carbon monoxide included. So it did yield me a different model, but it was less accurate. So here's a table of just comparing the data with the 2.5 and data without the 2.5. As you can see, this one has the carbon monoxide, and then this one has a higher root mean squared error and a lower R squared, which makes it a worse model because you want your R squared to be as close to 1 as you can get it, and a lower mean squared error is better. But it's not that much better. It's not like it's like a crazy accurate model, which isn't surprising because the data wasn't very correlated. And then I just made a couple of graphs with the linear regression line, and it's just not, it's just not working. I did try a couple of things. I tried transforming the data with log, and that did not help. And then, like I said, I didn't want to do a nonlinear method because they aren't linearly related. They're just kind of scattered all over the plot. So in conclusion, air pollution is not a good predictor of autism rates, which isn't surprising because, they think autism is caused by a lot of different factors. And maybe if you looked at, air pollution and hormones or just a bunch of different factors, that would probably be a better predictor for a model. And this is just my sources. That's it.
Thank you, Caitlin. Does anyone have any questions?
So none of the predictor were significant at all?
I did do a correlation, like I ran a correlation between the predictors, and they were all pretty like just closer to 0. One of them was a little bit better, I think. Let me see. Carbon monoxide was the best correlation, which is probably why it showed up in the second model that I did. But they predicted it. It just wasn't as accurate as I thought it would be, you know?
Yeah, thank you.
Yeah, I think that Vahid asked a good point. So at least this class is statistics class, even though the class focuses on more data analysis side. So you can see, for example, the F-test result for multiple linear regression. Then at least you can see if the model is significant or not. Also correlation, you can also test the number correlation coefficient and to see if it's significant or not. You know, it sounds the most of them are not significant, but at least it's worthwhile to see if it's significant. Yep. So did you see the F-test result? You have done the multiple linear regression, so the output includes the F-test for the entire model.
I can pull that up really quick. I don't have it right in front of me.
Yeah, that's fine. I think it's worthwhile to look into it. Yep. And I think that's as you mentioned, the time trend in the rate of autism. So the excluding time trend, for example, the deviation from the time trend of the autism rate may help to relate the autism rate and other environmental variables, air quality variables. I don't know if it works well, but yeah, it's worthwhile to do that. Yep.
Right. I found my F statistic and it says 6.039 on 3 and 28 degrees of freedom.
Okay, so probably it's, but F test, right? So then F value is 6 point something. So it's probably significant. Do you have the test result for F test? I think the R function have output of the p value of F test also.
Oh, the p value is 0.0026.
Okay, so somewhat, at least significant in total. Okay.
Mm-hmm.
That is with PM 2.5?
Yeah.
Okay, I see. Do you have any other questions?
I think this is super cool. The one question I had is, do you think that the rise in data, I don't know if this is the case, but could it be more people getting classified as autistic, even if the same amount of, people are born that way every year, just there's more and more information out there, et cetera, that could be the reason it's on the rise?
Right, that's like the classic question they've been asking is like, are there actually more cases or are people just getting diagnosed more?
That's what I'm getting at, yeah.
Yeah, I think people are just getting diagnosed more because more people know about it and there's more like, clinics open and more like, doctors looking at milestones and stuff like that. So that could definitely be, yeah, I think that's definitely happening.
Okay, very interesting. Thank you very much.
Thank you.
Yeah. So anyway, there are many missing variables, so we have to assume the time trend. Any other questions? Okay, so at least the data set is pretty good. So at least it's challenging, but you combined two data sources, so that is really made your project more unique. Okay, so the last one, Jacob.
Hi everybody, that's me.
Yep. So you can share the screen. Yeah.
Yes, and before I do that, I'm just going to share one other thing with you guys.
Oh, okay.
So I made a supplemental PDF for my presentation. It just has like pictures of the graphs that I'm going to be using. So I just sent it in the chat there. It also has any of the pertinent definitions. So if you guys want to reference those throughout the presentation in case I use it, and it's like, whoa, what was that again? It's all there for you guys. So I'm going to go through it very quickly, which is why I wanted to give that resource to you guys. But let's see, let us get started with this. Can you guys see my screen right now?
Yes.
Okay. Where is the presentation? Okay, can you guys still see it?
Mhm.
All right, perfect. So hello, everybody. My name is Jacobo Gomez. I am a third-year student here in the stats department, and I'm going to be giving a presentation on comparative clustering method applications in Michigan water quality, specifically with Upper Peninsula of Michigan. So let's see. So an overview of this presentation, I'll be going into the background information of what ecology is, what the data site is, going into like the data description of how the data is structured. And then I'll be going into the methodologies and empirical results for the two methods that I'm going to be focusing on, hierarchical clustering and topological data analysis. And then finally, I'm going to be talking about the conclusions that come from those two methods. So a little bit of background information on the topic. On the left-hand side, what we see is the graph of where all of these sites are located for my data set. And then that's also in the page for the supplemental text. But so the data came from Dr. Donna Kashan's lab. Dr. Donna Kashan is a professor for Wayne State University's Biological Sciences Department. And I have the wonderful opportunity to work with her. I've been working with her since July 2019 on both field efforts and data efforts for her data that spans over 10 years. So I'm fairly familiar with the data sets. If you guys have any questions, let me know. So the data was collected through upstream and downstream samples of 26 different water sites in Marquette County, Michigan. So looking at the Upper Peninsula, it's sort of like this region-ish, if I remember correctly. However, due to the inconsistencies within data, only 19 of those sites are going to be considered, and those are going to be outlined later in the presentation. In these sites, water quality variables over 21 were collected. However, due to inconsistencies as well, and some variables being collected later in the later years and not in the earlier years, were omitted. So that's why we're only going to be considering 7 of the variables. And those 7 variables with their definitions are on page 3 in section 1 of that supplemental document. Also, it is, when we're talking about ecological data sets, it's important to look at the timeline in which those sites that we're working with go through. So we started monitoring back in 2007. However, as it starts to get established, like we start to like learn more and more about like which variables we should look at. So my data set analysis is going to start at 2008 and then onward. So on the top, we see like the different years that are associated with any of the human pollutants that may have affected the watersheds in the bottom. Also, I'm going to use sites and watersheds interchangeably. Those are the same thing. But the human pollution that is going to be considered in this analysis is like surface construction all the way up to denuding forests. And then, of course, we also see like with COVID-19 beginning and with the restriction of labor, there may be some kind of shift in the data set. However, we're only going to be going up to 2019, so we're not going to be seeing that much of a shift due to that. Also, here's a sample of the data. So as we see in the left-hand column, we have data from 2008 all the way up until 2019. And on the right-hand column, we see that the label for the site. So this is site HMCA. And the golden columns on the top are the variables that we're going to be strictly considering on those 7 variables, which are pH, DO, temperature, conductivity, hardness, alkalinity, and DOC. And those definitions are in the supplemental text. It's not pertinent to know the definitions for these variables because they're not going to be showing up explicitly in the analysis, but it's always nice to know. So I have them there for you guys. So the objective of this analysis is to determine if there's a relationship between the watershed sites and the human pollution through multiple clustering analyses, such as hierarchical and topological data analysis. So first, we're going to go to the hierarchical clustering. So first, we're going to look into the definition of what exactly clustering is, and then we'll talk about hierarchical clustering. So clustering is the process of finding subgroups within a data set, and hierarchical clustering without a pre-specified number of clusters. Now, this is important for the ecological set because I wanted to make sure that the algorithm decided where the best clustering patterns would be. So I decided to go with hierarchical first as opposed to k-means clustering, where you choose the amount of clusters. In hierarchical clustering, you're going to do an analysis through a dendrogram. And a dendrogram is sort of like an upside down tree. So we have Henry on the right-hand corner to sort of visualize what a dendrogram looks like until I go into the actual dendrogram. So it's like an upside down tree with the leaves and the branches connecting all the way up into the trunk, which is the whole data set. Within hierarchical clustering, we're going to be looking at it's an agglomerative clustering method, which is a type of clustering that merges clusters together to ensure that there is a minimal increase in our linkage. And our linkages that we're going to be looking at are complete and average linkages. Those are very popular within the statistics realm. And considering this data set, I do focus heavily on the complete linkages, and I'll be going into why as we see one of the examples for the average linkages. The definitions for all of these methodologies are on page 3 in section 2. So I started the dendrogram. I just made like a random dendrogram at first, and as we can see, it is a hot mess. So we have a lot of observations here. We have over 260 when we include all of the years and all of the sites. So we couldn't really get any clustering ideas out of this data set, right? So I ended up looking into hierarchical clustering, and it turns out that when you have a smaller amount of observations, it actually is beneficial for the data. So you don't need like a huge amount of observations. So what I ended up doing to create a new dendrogram is I took centroids for all of the sites, for all the different variables that we're looking into, to sort of give like an indication of like what that site looks like throughout all of the, regardless of year. And when I did the complete linkage for this dendrogram, I saw that it was fairly easy to detect 7 different clusters. Again, talking about like the way I chose clusters is going to go into the conclusion as well, but there is some limitations to it. And what I did was I mapped all of these clusters together back onto, sorry, I'm going to go to average linkage first before I do that. So here's an average linkage diagram. Here we see that there is a potential for 3 clusters, but because like the middle cluster is like significantly larger than the other 2, I consider the complete linkage more. And that's sort of why I chose that one more, because of course, with hierarchical clustering and other clustering methods, we are doing an unsupervised learning. So it is subjective to the statistician. And when I did the complete and standardized hierarchical clustering based off of site centroids, we had like those 7 clusters, and each of those 7 clusters are color coded on the left. This picture is depicted larger in the supplemental text on page 5. And what we saw was there was typically a spatial similarity. So as we can see on this diagram here, the purple clusters, the dark blue, the orange, and the red are all spatially similar. And then as we start to look into the lime green, the magenta, and the brown, we start to see that there's some deviation away from the geographical spacing of these sites. So my first intuition is to think that possibly there is that because there's inconsistencies with geographic location, that there may be consistent pollution going on in these sites. Of course, I can't really say anything right now because we haven't seen like a pattern. So that's why more clustering methods are shown later. And the next clustering method that I ended up doing was the topological data analysis. So I'm going to go into the background for topological data analysis and a couple of the pertinent variables to talk about. So within topological data analysis, we have simplexes. So we have, like, for example, like a point here, an edge, and a face. And those are also known as a 0 simplex, a 1 simplex, a 2 simplex, and then also a 3 simplex, right? That we see here with the tetrahedron. And a simplicial complex is a combination of all of these simplexes together. So on the right here, we see that there's a simplicial complex there. With these simplicial complexes, you can also have voids and holes in the data where there isn't like anything filled in. So as we see in the pentagon on the left-hand side on the bottom, we have a hole. And this tetrahedron has a void in it because the inside isn't filled in. And those are actually very relevant within topological data analysis because that links back to homology. And homology is talking about the count of these holes or voids within a simplicial complex. So for example, on the left-hand side here, this pentagon has a homology of 1, right? Because we have 1 hole. Without seeing them visually, homology can be calculated through linear algebra methods. And topological data analysis does exactly that. It abuses this algebraic method for determining topological structures, such as homology and simplicial complexes, for a point cloud, which is known as our data. Topological data analysis has a specific method inside it that's called persistent homology. And that's a technique in topological data analysis that uses a gradient of radii. And from that radii, we can differentiate between what may be a potential topological structure, such as a simplicial complex, and what is just noise. Like if there's a lot of connections and it's just by a small increase, and it may not be a influential structure. To visualize that even more, I have a GIF of a persistence diagram on the right, and that red line is an increase of radius. And when we're talking about the radius, we're talking about this blue radius here. So as that blue radius increases, we start to get dots in our data every single time there's a new connection. And when there isn't a long connection, we have a long blank space, and then we make a dot when there's another connection. And this long space is an indication that we probably have some kind of topological structure there. So as we can see here visually, there's a high likelihood of there being like two clusters, and those two clusters are seen by this long blank space here, like right here. Okay, the persistence diagrams and the barcodes for this data, considering all of the observations with no centroids, are on page 6 and page 7 of the supplemental text. But as we can see here, we have like two of those long dots, and that's also translated over into the barcode, where instead of like having spaces, we just draw the line itself. So what we can see here, R disposes an n+1 barcode, which means that we're actually going to add another like 1 to the amount of lines that we cross over on a specific radii, which is this diameter here. And that's because we have like the trivial homology, where all of the points eventually at some kind of radius are going to be connected together. So that's taken out of this analysis. So what we can see here at this radii and at these radii here, we have a lot of like noise on this end, but this can tell us that we have a potential for 2 and 3 clusters within our data set. Okay, now we're looking at the complete linkage of this dendrogram, and we're looking at a site-specific centroid, and I can't really differentiate between where there may be a good point to cut like those 2 and 3 clusters that we saw in topological data analysis. So I decided to make a centroid for the years. And when I made centroids over the years, regardless of site, for a complete linkage, what I saw was that there's an arbitrary point that we could choose right in the middle and cut this dendroid into 2 parts. Right, so that's sort of like reminiscent of the topological data analysis that we saw with that barcode of 2 clusters. And we can see that this is also, when we map these onto the timeline, we can see that there's a definitive measure within our timeline. On the left-hand side, we have the 2 clusters that link to heavy human pollution advancements, and on the right-hand side of this dendrogram, when it's cut, those are also, it's sort of like the aftermath, or before there is a lot of human pollution, or there's only very minimal parts. So you can see that with the red, the light blue, the pink, and the orange, they're sort of on the outskirts of these 2 lines, and this teal and the purple are on the inside, where there's a lot of human pollution going on. Okay, so for our conclusion for the data set, what we could see is that when we have shifts in clustering, it may be able to push us more for analysis that there is potential pollution going on and affecting these sites. We cannot say definitively without more exploration, because of course with unsupervised learning, the objective is technically to find like an exploratory of our data, to sort of get a visualization to see if there's something worth going into quantitatively, because we're looking at it from more of a qualitative standpoint. Also, as we saw, we can see small decisions within our clustering can have a large effect on our results. So even though I chose to do the 2 clusters, and I chose to do the 7 clusters in the complete linkage, different methods within choosing where those clusters lie may give me a completely different story, right? And that's why we try to see patterns within our data set to help validate that there are in fact these clusters. Also, these current clusters that we've chosen should not be taken as a complete truth. Again, going back to the small decisions talk. And also it is important to note that we did optimize the robustness of our data analysis through the data preparation, specifically when going into those centroids. The centroids gave us a more robust analysis. Further analysis of this data set through a spatial recognition and through like a qualitative standpoint can include a k-means clustering. So as we saw, there's a potential for 2, 3, and 7 clusters within our data set. So possibly running through this analysis again with a k-means of choosing 2, 3, or 7 clusters may be beneficial to us to see a consistent pattern. Also, we could do a treated principal component analysis on this data. When I first did a principal component analysis, that's what I originally wanted to do with this set. It came out fairly inconclusive because we ended up with 7 variables in the end, and those variables didn't all of them had a significant impact on our variability. It sort of came out as a linear line as opposed to a curve, so we couldn't really reduce the variables. But going in and rescaling the variables using a different method, such as an ecology arcsine, is a very applicable transformation. We may be able to create a principal component analysis. And the reason why I'm not giving up on PCA yet is because as we saw in this analysis, there is a way to like cluster these observations into smaller observations and clusters.
So it exceeded time. So yeah, okay, maybe you can, yeah.
Oh, that's it.
Yeah, okay,
I'm done.
Okay, great. Yeah. Okay, so do you have any questions?
I got a quick question. When you showed your data table, one of your rows was missing the conductivity. I was wondering what you did with the missing values since you're so familiar with the data set.
Oh yeah, no problem. So there are different ways that you could treat like the NA data for this specific analysis. I ended up just taking out those points, like taking out like those year rows, mostly because there weren't a lot of them. As we can see in this site, there was only one of those years. And that was that was something that was very, I guess, uncommon for the sites, especially for those 7 variables, which is again why I chose those 7 variables, because they don't have like that many omits. In previous analyses with this data set, I ended up doing interpolation methods. So that definitely is a method that I could have used for this in further analyses.
Okay, very cool. And then one kind of follow-up question on that. In general, would you say that these columns really specify that there is pollution, or are some of these things natural for like conductivity to go up and down?
That's a great question. So in past ecological sets and in the analysis that I've done for these, we ended up doing like linear regressions, and with what is tabulated within previous results, the ones that have the most influence in deciding if there is pollution are conductivity, pH, and DO. So those 3 are like the most significant that when looking into if there's a type of pollution within the sites. But of course, all of these have an impact. So that's why I also really wanted to include those 3 variables, even if there were some that were missing.
Okay, very cool. Thank you.
No problem.
Okay, so just one comment. So the dendrogram for the different sites, the 19 sites, you made the 7 groups, but I think the dendrogram should be cut at some horizontal line. So we have to be consistent with that. Maybe, maybe the most left 2, that is split at 4, right? So probably it should be split before we split, for example, the most right 5 sides, right?
So like down this line here?
Yeah, maybe a little, maybe if you want to have, for example, 5 clusters, probably you will cut at 3. So the first group, second group, third group, fourth group, then maybe fifth, maybe before that, yeah, maybe the BBA and HMCB, then maybe as 4 groups or something. So I think that should be consistent with dendrogram. So for example, the S510F and S510G is split from the other 3, the 550C, 51, but that is really lower point than the split point of BBA and HMCB. So I think that BBA and HMCB should be split first before you split the right 3 groups, right?
Okay.
Yeah, but anyway, yeah, but overall, I understand. Yeah, there are several suggestions for the presentation on the next Monday. At first, so I would like to see the more comparison between different models. So, for example, if you do the linear regression and the maybe tree-based method, then you cannot directly compare, but you can compare those with the error size, for example, RMSE, and the using cross-validation, right? So the out of sample performance prediction, performance comparison, that is key part in the data analysis for machine learning methods. So that if your project includes the more than 2 models, then certainly that it's worthwhile to compare those models. And also if your slides, and also avoid R codes when possible. So especially if you include too much R codes, it takes time for audience to understand your slides. So just keep it simple and beautify your slides. I think those are these two the main 2 comments, and also the statistical interpretation, especially for example, valid, make some scatter plots, and I think there is one outlier, right? So probably you have to remove that point. But without making the scatter plot, we cannot get that kind of information. So the descriptive statistics is really essential before applying the more advanced statistical methods. And more importantly, the next time we have 6 presentations, and they probably will need more than 75 minutes. So just make you available at least until 8:50. I'm sorry about the extension, but instead that we don't have the the final exam. So just make you available from 7 to 8:50 on Monday next week.